So, wrong thing there. A little bit of notation. We have already seen this notation for higher order derivatives because technically we've already done part of this section, because we looked at, when we were doing implicit differentiation, we looked at taking a first derivative and then a second derivative, right? So we've already seen this. You could keep going, and these 2's could change to 3's or 4's or 5's. You could take the derivative lots and lots of times. I don't know that I've ever seen a implicit problem that went past the second derivative that I can think of there. Now, sometimes if it's something they can give you in regular function notation, they may ask for a higher derivative than the second derivative. So it's just the number of tick marks. When you get past 3 tick marks here, they will start putting this up here in a set of parentheses, because your tick marks get too crazy here, so it might be like y to the 5th or y to the 9th, but it's going to have those parentheses around it, and you're going to be given a function so that you know it's not like just asking you to raise something to the 5th power. So if you see this notation, particularly, they're less likely to use y notation if they do that, and more likely to use this f notation, which lets you know that it's a derivative and not the like raised to the power there. So let's look at some examples. Okay, these can be super duper easy, such as our first example here. So our first example, we've got f of x equals 6x squared minus 3x plus 2. They're asking us to find the second derivative, which means we must take the derivative twice. When you do this, you need to label everything. Like, you might get one this easy. Label it. Because one of the points is going to be for that first derivative. And if you don't write it down because you did the whole thing in your head, you're going to miss that point, right? So write it down like that, right? First derivative is 12x minus 3. So what is my second derivative? 12. That's it. There's your answer. What would the third derivative of that be? 0. What's the fourth derivative? Still 0. Anything past that would be 0, right? So those, super simple. 2 is a little harder, but trig sort of like repeats itself, right? Like the derivative of cosine is negative sine, and the derivative of sine is negative, or is cosine, and you just keep on like going, right? So here they're asking for the fourth derivative, so we would start with f prime of x. Now, this is a chain rule problem, okay? Because you've got to take the derivative of cosine, and then you've got a 3x on the inside. If it was like 3x squared, it'd make this a hard problem. But it's just 3x, so it's not too bad, because what is the derivative of cosine? Negative sine of the stuff that was in there, so 3x. But then we must multiply it by the derivative of the inside, which is 3. So our first derivative ends up being negative 3 sine of 3x. To take the second derivative here. What's the derivative of sine? Just the cosine. The negative 3 stays there because it's just a coefficient. I've got cosine of 3x, but I must multiply that by the derivative of the inside, which is 3 right there. So now I've got negative 9 cosine of 3x. You can kind of see like a pattern starting to develop here. F triple prime here. There. We're going to have the derivative of cosine would be negative sine. That negative is going to turn that 9 to a positive. So we'll have positive 9 sine of 3x. But again, we got to multiply by the derivative of the inside, so we're multiplying by 3. So we get 27 sine of 3x. And our last one, the one that they're asking us for, derivative of sine is cosine, so we're going to have 27 cosine of 3x, and we must multiply it by the 3. This is the derivative of the inside. And 3 times 27, it's going to be 81 cosine of 3x. That'll be our answer there. They like to give you these types. If they ask you for like 4th, 5th, 6th derivatives, something like that, a lot of times they'll do it with something like this where it's like a cosine where it's kind of repetitive. They like to use e's a lot because e's are themselves and they're pretty easy to keep like taking the derivative of. They're super duper easy if they give you just a polynomial there to do. Okay, questions? They might. They might. So they might ask you like 5th derivative there. And if they do, like as soon as you hit 0, you know it's just going to be 0 from there on out in that case. The one you see more is one like this where you do actually have to like keep doing the work. But I have seen some where they're asking you for ones that end up just being 0. Okay? This one is one that we have done before because well, sort of. It's implicit differentiation, but is this really implicitly defined right here? Not really, right? Like we don't have, like our dy dx when we take our first derivative is just over here. Oh gosh. Let's erase that while we still can. So if I take the derivative of this, I'm going to think of it as x plus 2 to the 1/2 power. So that is going to be 1/2 times x plus 2 to the negative 1/2. And then I must multiply that by the derivative of the inside, which is just 1 here, so you really don't have to write that if you don't want. Now, normally, like if I was evaluating this, I would go like change this to where I moved it back down to the bottom. But we've got to take the derivative again. So it's really easier if I just leave it as an exponent right here, right? So now if I take the derivative a second time, right here, that's x plus 2 to the 1/2. So, this is telling you what number to plug in at the end. Okay, so that line really should be longer, but this is the best I could do on like typing it because I couldn't figure it out. That line is usually like a little bit longer, and that x equals 2 is like down here, like more like right here, right there. But that's just telling you the number to plug in at the end. But you want to find the derivative first, and then you'll worry about plugging in that number. So if I take the derivative again, I will get negative 1/4 x plus 2 to the negative 3/2, and then you're multiplying by the derivative of the inside, which is just 1. So you really don't have to write that 1 if you don't want. Now I need to plug a number in now, so I would try to get rid of my like negative exponent. So I'll have negative 1/4 times x plus 2 to the 3/2. And then I would probably even do this, negative 1/4, and I would change it back to the square root of x plus 2 cubed, like that. And so they just want you to plug the 2 in. So you will have negative 1/4 square root of 2 plus 2 cubed right there. You could stop here on the FRQ question, but this is a lot of times you're either going to need to use that number for something or it's multiple choice. So we got the square root of, that's going to be 4 to the third. 4 times 4 times 4 is going to give you 64. So you get negative 1 over 4 times 8. So negative 1 over 32. So that one looks like it's sort of like those implicit differentiation problems, but you don't really have to do anything special for it because it doesn't have a y like mixed in with your x's for that. Okay, let's look at this one because a lot of times we have trouble with these problems where we've got like f of g of something, or you know, it's defined where we don't have a function for part of it. So what rule am I going to have to use to take the derivative, the first derivative here? Chain. Because I've got g is my function on the outside and 2x to the third is my function on the inside. So for my first derivative, h prime of x, I will get the derivative of g will be g prime of, I'm going to leave the stuff on the inside alone, 2x to the third. But then what do I have to do? Multiply by the derivative of the green stuff. So that will be 6x squared. Okay. What do I need to take the second derivative here? Gotta use product rule, right? Because I've got this piece right here is being multiplied by this piece right here. And within that product rule, I'm going to need a little bit of a chain rule because I got like an inside of a function right there, right? So the second derivative here is going to be the first part, which is g prime of 2x to the third. Leave it alone. Multiply that by the derivative of 6x squared, which will be 12x, plus sign 6x squared. Now we got to take the derivative of g prime of 2x to the third. What is the derivative of g prime? G double prime of, leave the stuff on the inside the same, 2x to the third. And then I must multiply by the derivative of the stuff on the inside. What's that going to be? 6x squared. Now, they will probably clean this up a little bit and write it maybe like this, 12x g prime of 2x to the third plus, here you can multiply 6 and 6 together to get 36, and the x squared times the x squared to get x to the fourth, and then you'll have g double prime of 2x to the third. And they'll probably stop there. You could factor out a 12x if they wanted to out of both of those, but probably stop here. Chance they make you plug a number in after that.
You can pull out a 12x part of 2x and 2x.
You can only pull out the 12x because this is g prime and this is g double prime, and those are not the same.
You can't pull it out like one prime after another prime.
Right, you cannot. So like, you cannot like treat that like it's a first and a second power sort of, and like take a single prime out. So you would have to keep those separate. It would be okay here though to like take the 12x out, so you'd have g prime of 2x to the third plus 3x to the third g double prime of 2x to the third. So that's as far as you could go. You can't like take one of the primes out. That doesn't work the same. Everybody okay here? All right, we got one more like application situation we need to look at because we've already talked about the fact that if we have a function that gives us position, sometimes it's like the position as you're moving like left and right. One that we've seen and we're going to look at here a few times is like the height of a projectile. That's a position. That's how high you are. So if I have a position graph, that position graph would have time here, and it would have, I need to do this so my pen's a little bit smaller. And then I would have position or distance here, right? So if I take the derivative of that, that would be change in position, which is really like a distance, right, over change in time whenever I take the derivative. What is your change in position or change in distance over time? Velocity. So if I think of what my velocity graph would look like, I've got time here, and I've got velocity here. So if I want to think about the slope of that, I'd be thinking about change in velocity over change in time. What do we call the change in velocity over the change in time? That is your acceleration. Right? So it's all linked together. So this is why, like, a few of you have had physics, right, or are taking it now. But if you take physics, you are taking algebra-based physics, because I know they didn't sign you up for calc-based physics if you've never had calculus, and you guys haven't finished it yet. But you can either take algebra-based physics where they give you like all of these formulas already worked out for you, or you can take calculus-based physics, in which case you don't really need a new like equation for velocity because it is just the derivative of your position equation. So I never took algebra-based physics. I only had calculus-based in college. Every once in a while, some of the kids will like come ask me questions about like their algebra-based stuff, and I have a hard time with it because for this stuff, I know how to do it like the calculus way. So those of you that are in physics, Reese, you got it, or you've already had it? You have it now? Yeah. Rowan in there too, or has he already had it? Last year. Has anybody else had physics? You had it, you have it now? Yeah. Like, whenever you do position, velocity, acceleration sort of stuff, like they give you the formulas. Kind of pay attention, like it's the derivative there. Let's look at units real quick too, because those are important. Okay, so if I'm measuring position, in, I'm going to pick a unit just so we have one to work with, right? So it is distance. What is your favorite way to measure distance? As a good American will say, miles. Okay? And then, what is your favorite way to measure time? Particularly if your distance is in miles. I'd go hours if my distance is in miles. Okay? So, if you have position and you're measuring that in miles, what would your units for velocity be? It'd be miles divided by hours, so it would be miles per hour. Okay, so that means on this graph right here, I got miles per hour, and then I got hours here. How do I measure my acceleration? What are my units there? Miles per hour per hour. Or you can think of it this way, miles per hour divided by hours. I'm going to put that over 1. Dividing fractions is easy as pie. You're going to flip the second and multiply. How could I write that? Miles over hours squared. So you could also say miles per hour squared. Now, that's specifically for miles and hours, but you could replace miles with any type of measurement for a distance. It could be feet, it could be meters, it could be millimeters, whatever. And same for the time. You can replace hours with seconds, minutes, days, whatever. Anything time here. So positions measured in just straight distance. Velocity is going to be distance per time. And then acceleration is distance per time for that. There. So let's look at a problem. The height of a projectile launched from the ground is given by negative 16t squared plus 120t, where height is measured in feet and time is measured in seconds. A says write an equation that gives the velocity of the projectile at any time t. So if I know what h is, that is my height, that is a distance from the ground, how do I find the velocity? Derivative. So h prime of t would be my velocity. I like to call it h prime of t and then say v of t instead of just saying v of t. You're probably going to get by with it on the AP exam, but this shows me I know that those two are related. I took the derivative of h to get what I'm calling v, which is velocity. So that would be negative 32t plus 120. It is. That should say acceleration right there. Oops. All right, so if I want acceleration, I could then take the derivative of what I just had, right? So I could either call it h double prime of t, or it could be v prime of t, or if you want to, let's switch it to an a because that's what we usually do for acceleration. What's my acceleration? Negative 32. And the units on that would be feet per second per second. This is your acceleration due to gravity on Earth, which is constant. That acceleration due to gravity is always negative 32 feet per second per second. And that's like actually the right number for that. I'm not certain if it might be simplified a little bit for problems here, like it might be negative 32.00072 or something. I'm not sure about that. But for calculations, we will do definitely close enough for us here. And that may possibly shift just a tiny bit based on your altitude or something, but negligible for anything we would calculate here. There. So we got both of those equations. So the C says, how long was the projectile aloft? I took this from the worksheet that you're going to have today to make sure we knew what this means whenever it says aloft. In the air, right? So if I want to know how long the projectile was in the air, what do I need to do? When does it become not in the air? When it hits the ground. What is its height when it hits the ground? 0. So I could actually use my height formula, which was negative 16t squared plus 120t, and I'm just going to set that equal to 0. Now, if I want to solve that, what would I do? Factor out of t. Negative 16t squared plus 120. And then I can set each one of these equal to 0. Now, t equals 0 is not my answer. That's when it was on the ground when it started, right? Oh, thank you. There. And then I'll have negative 16t plus 120 equals 0. So that'll be negative 16t equals negative 120. I'll divide by negative 16. Oh, let's see if I can do this without. You're going to have, definitely be like negative 60 over, well, actually, it's going to be positive. 8. That'll be 30 over 4. That'll be 15 over 2. That'll be 7.5. Does that sound right? Okay. So 7.5 seconds here. Right. T of 0 doesn't work because that is, like, it was also on the ground whenever it was thrown into the air. So that's your, like, beginning piece. So the one we want is this one over here. Then D asks us what the velocity is when it hits the ground. We did this with our rockets, right? We were doing this with our rockets. So what do we need to do for that? Not H. We need V. Well, actually, what did you say? You said H prime. Yes, I was hearing H there. Yes, H prime of T, which we could also call V of T. There. So, yes, our you can either call it H prime of 7.5 or you could call it V of 7.5. So that is just going to be negative 32 times 7.5 plus 120 there. And I am going to resort to the use of the calculator here. This is negative 240 plus 120, and you get negative 120 feet per second there. So we kind of like went ahead and did a little bit of this because we had the opportunity to go do the rockets, right? So this is sort of a reiteration of that there.